On today's episode,
Okay, as you can see, they are using the heating mantle, which we don't. Okay, heating mantle causes accident because this is supposed to be used with the controller, which is a separate unit, and people do forget hooking it up. Okay, so when you connect this unit to the electric socket directly, this will receive the maximum voltage, more than maximum voltage this can stand. So soon it will start burn. Say though you have the controller, when you choose this wrong size, it's not ideal because the heat is supposed to get transferred from all area inside to the round bottom flask, and as you can see, they're not even touching. So it's a poor usage of um, tools in this reaction setup. For now, only thing I want to say is the second clamp here is there to stabilize the setup, okay? But this clamp has to be somewhat loose, so you can easily bring the whole thing by loosening up this part and bring things up and down easily, or just take this away quickly for some emergency situation. So make sure you know this part, the clamp hand, should be loose.
of blowing things up in chemistry class, we have what do we have? Sulfuric acid.
And they have a right amount of the liquid, right? Which is about half or less of the round bottom flask. And I don't see any magnetic stirrer.
And potassium rhodide, one butanol. We have a
And as you can see, the water flow is not steady, which will provide the poor cooling. Okay. And they're literally heating up actively, so they should have a good cooling going on. Otherwise, some toxic vapors gonna escape, and you may breathe in. You don't want that.
water mat showing things down. Lloyd, I did not blow up anyone when we next.
And this student slash TA does not wear goggles. Not good. Goggles are thrown on the table. That's right.
I don't think it's just blowing out like it's like that bump, like it's not going out completely. Is that supposed to be like that? I
Nope.
think so, because
It's
it
not
didn't
supposed
have
to
a
be like
string
that.
out there, Lloyd. And I think it wasn't coming out in a string. Then.
The lab is pretty clean.
Going nowhere. Is this what we're supposed to write our things? I don't know yet.
And this lady doesn't even wear goggles and glasses. Oh my gosh. And the cell phones are on the table as well. And they said they're using sulfuric acid. What if you have a drop of sulfuric acid on the bench? You thought that was just the water, or you didn't even did not notice. You put your cell phone the side where you put your face on when you talk. Imagine this is a sulfuric acid. I don't know you studied sulfuric acid during the safety training video watching, but sulfuric acid can burn the wet paper. Literally, you have a wet paper with a lot of water, right? And you drop couple sulfuric acid drops, it burns. You don't want to have it on your skin, on your face especially. It just bothers me, people doing this.
Y'all? I'm still as lost as y'all. We have some more.
That's the controller I mentioned earlier. And no one's wearing lab coats. This is 2019, right? It's not 1919. This is 2019. It's not like years and years ago when people do not really reinforce the safety. That's what they're doing, teaching practical skill. Okay, reaction's done. You see they lift things up, right? And then start cooling it down. Then you'll see organic layer and the aqueous layer because you had sulfuric acid. They're expecting getting some solid. That's where they sound worried. But it's hot. We went over this, right? It's hot. That's why it's dissolved. And you have some amount of water. That's why you're not getting all of the solid yet. Hopefully they get something. But their product is the organic layer, not the solid. They're supposed to get, so they're getting solid here, so they're happy.
So what?
But their product is not solid.
How perfect those crystals are, y'all. They're like perfect little squares.
It's nice crystal. It's really crystal. It's not just a solid. Pretty good, but that's not the product.
The crystals are falling out.
So the observations are made, and you should put them on your.
And it won't affect our. Okay. Okay. So we're gonna add some water.
That'll be fine, yeah, or you can leave it and let them write it down.
We'll just write it down for you. Oh, you're right.
We're adding extra water,
It looks like it.
so they want to
The
dissolve
top layer should still be there.
You think
all
we
the
could
solid.
stir?
Yeah.
Because they want to perform
It
extraction.
may not work, so I better not make it drink too early.
You're like, it might not work.
We'll just wait to see if it works first. See, your layer's still there.
Yeah. So we washed it with water, and then we.
After a few extractions, this is one of the late stages of extraction. You have about equal amount of the water and the organic layers. And it's time to dry your organic layer. I don't know whether they're gonna show it or not, but it's time to dry.
So now I'm gonna measure it to see how many. It says five.
The school does not ask.
What if we don't have 5 milliliters?
The solution doesn't look clean yet. It's cloudy, meaning you have lots of water droplets.
We have like 4.5.
I hope.
Hello everyone, and welcome back to the lab. In this video, I'll be preparing 1-bromobutane. I will use 11 milliliters.
So primary alcohol, strong sulfuric acid, concentrated, extremely dangerous, and also very strong acid, as strong as a sulfuric acid, NaBr. But we are using sodium bromide instead of HBr. Okay, sodium bromide is just a salt. It's not acidic. It's more safer.
Of N-butanol, 7.4 milliliters of concentrated sulfuric acid, and 17.5 milliliters of concentrated hydrobromic acid. I first added the hydrobromic acid to a 50 milliliter round bottom flask.
Initially, they had pretty good amount in the small round bottom flask with a stir bar, tiny one that fits the capacity of the round bottom flask.
Next, I stirred the
and their heating mantle again is too big.
mixture while slowly adding 4.1 milliliters of
Nice
concentrated
stirring
sulfuric
they
acid.
have.
To keep the mixture cool, I placed the flask in an ice bath.
The solution's already red. I'm not red. I don't know, orange or yellowish. That's because the reaction already created some colored impurity due to the high temperature. They should have cooled it, not heating initially. They should have done this addition of the sulfuric acid um, in the ice bath initially. Due to the lack of that awareness they have, impurity already formed.
After this, I poured in the N-butanol. This doesn't need to be kept cold, but I just left it in the ice bath while I did this.
We're not going to add liquid this way.
Finally,
and
I
this
added
much.
3.3 milliliters of concentrated sulfuric acid.
And I hope they don't boil this thing. It's too much.
The flask was
They do
lowered
boil,
into my
right?
oversized heating mantle, and a condenser was placed on top.
I
This is
cannot
preparing for the
believe
reflux that will take place next.
so many places teaching students wrong things.
Water flow was started in the condenser, and the heating mantle was turned on. Once the contents of the flask started to boil,
Yeah, they do this aluminum foil because heating is not as effective. It's also because they're not touching heating mantle and the round bottom flask.
I started the clock and refluxed the mixture for 3 hours. Once the 3 hours was up, I turned off heating and let the flask cool to room temperature. You can
So this outcome is much darker compared to the previous school, right?
see that 2 layers formed, the upper layer being our product. I set the flask up for simple distillation to recover the bromobutane. The mixture was distilled until no more oily and cloudy drops came over.
So instead of doing extraction, they've done this distillation. They were able to get a clear solution. So as you can see here, you can pick and choose method to purify and isolate the product from the reaction mixture. If you know what you're doing, you can come up with your own method. What we do is that we are doing extraction more carefully.
After this, the distillate separated into 2 layers, and there was only 1 layer present in the boiling flask. The bottom layer, seen here, is the bromobutane. It was then washed with water, hydrochloric acid, water, sodium bicarbonate solution, and lastly water.
So why sodium bicarbonate solution? Because you have acid, you need to quench that.
These steps aren't included because I have a feeling that all of my viewers know how to use a separatory funnel.
Yep, it's a lab 10, so they should
Following
know.
the final washing, the cloudy bottom layer was transferred to a vial containing some calcium chloride.
Which is a drying agent, right? This person did not forget drying the layer.
As you can see, after a few hours, it had cleared up completely.
Yep.
The liquid
Even after distillation, this person did that.
was transferred to a 25 milliliter round bottom flask, and a stir bar was added. Unfortunately, I spilled a bunch and got some calcium chloride into the flask.
Spilled.
After a small amount of forerun, the product came over between 95 and 98 Celsius.
Pretty good.
This boiling point
Second
is almost 10
distillation.
degrees too low, and I attribute this to my crappy
This is
thermometer.
too fast, right? The distillation must be done 1 drop per second or slower. The slower the better. This is way too fast. Too much heat.
Given the properties of a liquid and the chemicals we put into the reaction, there's really nothing this could be other than our desired product. The final yield was 7.96 grams, or 48.3%. The disappointing yield is a combination of small scale and me spilling a bunch into my heating mantle during the transfer step.
Very honest person.
This has been the preparation of 1-bromobutane. Thanks for watching, and don't forget to subscribe.
And let's see what we do at York. It's about the same, but not exactly. I hope you see me. Yes, you do, right? Yeah. So the reaction Sn2 should have strong base, but it's not strong base. Br minus is a weak base. And you should have a primary. You do have a primary. And you gotta have a good leaving group, but you don't have a good leaving group. But we can turn poor leaving group to the better leaving group by adding H plus from sulfuric acid. So this sulfuric acid is not a reagent, it is catalyst. Catalyst, the chemical, is a chemical that is only used to lower the activation energy and making the reaction rate faster. Then you get the chemical back at the end. So you're using H plus, but you are getting it back after the reaction. All right. So anyway, H plus making water out of OH, and you just made a good leaving group. You have a primary. Only thing you don't have is a strong base. But Br minus is a stronger base than water, so it's good enough. So that's what it means when they say strong base for Sn2. They don't really mean strong absolutely, such as a hydroxide. They meant more unstable, stronger base compared to the conjugate base of the leaving group. Okay, in this case, the conjugate base leaving group in the product side is water. So compared to the water, Br minus, the negative ion, is more unstable and it's a stronger base. So it's good enough. But absolute scale, Br minus is a very stable conjugate base. That's what it makes HBr, strong acid. Strong acid's conjugate base is a weak acid. Remember, HBr is much stronger than HCl. So Br minus is very stable. When Cl minus from HCl is very stable to make HCl one of the strongest acid, the Br minus is even stronger, more stable. So HBr is a stronger acid. So you know how stable Br minus is, but that's more basic than water. That's why Br is a strong base, although it's not really strong. You know what I mean now, right? So those concept of terminology in the book, you have to understand properly. Then you have no objection for Sn2 with these chemicals. And you got the non-hydrogen bonding oily substance from somewhat water-soluble polar-ish. Not extremely polar, but you have more non-polar side, but overall it is polar enough to have decent solubility in water. But this one does not dissolve in water at all. Okay, this is how we do reaction. Better than any of those two, video places. We have Ramadan flask, and I'm not saying how big it is because I explained during the lab, right? Because we don't have to. We all know as a common sense, the total volume of everything has to be less than half of the round bottom flask. There we go. Okay. And then stir bar, hot plate, and then one clamp around the neck of the round bottom flask, straight up, after adding all the chemicals, right? Straight up, and then loose clamp. Then we have the thing open. The system's open system because you are heating. Then you have a sulfuric acid up there in the separator funnel. We're not pouring into. We are doing drop-wise. Again, we did it in the in-person lab, saying you don't want to add acid, quick, because then it's too exothermic. If it is exothermic, elimination reaction is going to be promoted, and that's your byproduct. The exothermic gives the heat from chemical, and then it raises the temperature in the flask. If you drop-wisely add, then the emission of the heat is less, and then you have a more time to dissipate and lose the heat to the around surroundings. Therefore, you can minimize the side reaction. Okay, so this is our setup, your college's setup. Every single thing we do here is outcome of careful not renovation, but upgrade changes that we made over the year. And as you can see now, we were not able to compare to other school until pandemic. But when we opened up, we realized that your college has a much better standard and careful design for the things for our student. And I became much more happier and confident for what we are doing and what you guys are learning from your college. And I am there to open up and compare with the MIT ones, remember? I'm not ashamed of what we do, when even compared to MIT. So yeah, we have that, but we are not having reaction right away this way, okay? There were 4 stages of organic synthesis, if you remember. First, planning, right? And do synthesis, then isolation and purification, then identification, right? Before you submit for the testing, like a toxicity testing or application testing, quality testing. So first, planning is a pre-lab report writing process. You've done that already, and that process we're gonna learn more in depth in organic 2. Assuming that we are not done any reaction ever in the human history. So you are making your own procedure as if you are doing in the professional lab. So we will learn how to do the first step, okay? But you are all 1 students. We don't do that. We copy from textbook or some previous PowerPoint that I posted on Blackboard. You copy that. Then you are actually running the reaction. That's a synthesis step, the second step. First, you place these things in the round bottom flask before you stack up the column, right, with the stir bar. Then you add 10 milliliters of water and the butanol. They don't react because butanol's having poor leaving group, and Br minus is not HBr, so it's not able to activate the OH yet, and Br minus is not able to kick out OH minus because OH minus is not as stable as a Br minus. So Br minus is a weak base. And you might want to say impulsively, wait, you said earlier Br minus bromide is very strong base. That's when it's compared to the water. Okay, here you are compared to the OH minus. Why? Because you did not add acid yet. Without acid, nothing happens. That's why we are mixing all of those things safely. Then you put the round bottom flask in the ice bed. Remember the first and second video I was telling? You should have done it in the ice first before it forms byproduct. So this change is made few years ago. This is our own procedure. So in the ice bath, you cool down for a while. You have to wait until the whole solution becomes cold enough. Then you add sulfuric acid from the top slowly, and the solution is cool. Okay, so you gotta have an ice bath on top of the stir bar. I'm sorry, stirring hot plate. The stirrer will stir the things with the ice bath as you add this thing. Make sure you see the tornado whirlpool thingy in the liquid layer, indicating sufficient mixing of the exothermic H2SO4. Then, after completion of the sulfuric acid addition, you remove ice bath. The solution is going to be still cold. No elimination took place, okay? Then you start refluxing, start warming up for 30 minutes. That's the reaction. Then we move to the third step. After 30 minutes, normally we check TLC, but we don't do that in Orgo 1 for monitoring the reaction, because TLC is specialized to checking how many components are in the mixture. And then you start workup, which is basically isolation and purification with a quenching step embedded. So you cool down to the room temperature. Solid may form. Remember a student asking in the first video, oh, square, why my crystal is a square? That kind of thing you expect, and carefully transfer into the separatory funnel for extraction and add 10 milliliters of water. So you want to dissolve everything polar into the water, remove it from organic, which is this compound. Every water-soluble stuff, okay, will be dissolved, except this guy, dissolved into the water. So that extraction is going to get rid of most of the garbages. Then you shake and separate organic layer and wash organic layer with water, making sure you can wash away more if there is any left over. And then saturated NaCl. The saturated NaCl is more polar, so it's making sure anything with a little polarity, you can actually dissolve them out. So assuming everything is gone, you can dry the organic layer with a drying agent, then filter. Which filtration technique? You guys know, right? I told you how to choose which filtration techniques you have to choose. When you keep the liquid as your product, you do gravity. When you keep the solid as your product, then vacuum filtration, and so on. So you filter into the pre-weighted vial, because then you know by weighing the whole thing, you know how much you got how much product you got. Okay, so even the last step they haven't done properly. So I hope you feel good about learning at York. Once you've done, if you run IR, right? This IR of the reactant will have an OH peak above 3000, and in the product you should not have that one. Instead, you have some peak for this polar functional group, CBr, around 600 to 700. So if you double check your dry lab, you know what I'm talking about. So make sure you know that in preparation for the final exam. That's it. This is our last online lab, and we do 4, 5 synthetic lab. So we do couple in person. Therefore, I think you can run this reaction in real life using the experience you get from in-person synthetic lab. And also you recognize how the other techniques for the purification we learned in the first 6, 7 experiments are playing its role in the big scheme of the synthesis. I also went over this during the dry lab. So have a great day, and I will see you guys in the lab. And soon we will have a practical exam